Okay, good morning, everyone. My name is Daniel Reyes from the Instituto Militar de Engenharia in Rio de Janeiro. At first, I would like to thank the organizer for giving me the opportunity to talk about this work. This related, basically, related to the charge density orders, the interplay between charge density orders and superconductivity. Okay, so these people are my collaborators. This guy here is Ney Lopez from the UERJ in Rio de Janeiro. This is Professor Nathanael Costa from the UFRJ. This is Professor Christopher Thomas from the Universidade Federal do Rio Grande do Sul. And this is Professor Múcio Continentino from Rio as well. Okay. All right, yeah, there is. Okay, basically our results are discussed in these two papers here. The first was published in 2021, and the other one was published recently, okay? Okay, just let me, maybe this is not working here, okay. Okay, this is overview of my talk. First of all, I'm going to talk a little bit about the experimental motivation behind this work, essentially about the transition metal dechalcogenized, named TMDs, okay? Then I move to some previous theoretical work to deal with this interplay between different charge density orders. Then I will introduce the Hamiltonian that we use, and finally, the results and the conclusions. Okay? Okay. Before starting, let me, maybe I could remind you what is charge density wave. Essentially, charge density waves is associated to the periodic modulation of the electronic density, right? So it was proposed initially to come from the electron-phonon interaction. Also, I must say the commensurate terms means that the wave vector modulation matches exactly the lattice. For instance, in a square lattice, it would be this wave vector named Q, it would be pi pi. Okay, pi pi over the lattice parameter, okay? And incommensurate means basically that it is slightly different. Okay, so now here I show this very known result, this experimental result. This is a very known TMD compound, copper dope, titanium diselenite, and we can see from this experimental phase diagram, this is temperatures as a function of pressure and copper intercalation, and we can see the different phases, for instance, charge density wave here, and this is the superconducting dome. So after reading this paper, we get two important insights. First is that this charge density wave phase here is, the nature of that is commensurable, and on the other hand, the superconducting phase here can be explained by the BCS framework, okay? Okay, so later on, even for the same compound, in 2017, it was reported this phase diagram, okay? Again, is temperature as a function of copper intercalation. And again, we see for high temperatures, a commensurate charge density wave, okay? But at low temperature, we see an incommensurate charge density wave emerging near the superconducting dome. So from this experimental phase diagram, we could ask the following. So what kind of interplay is there between these phases? So they compete, they coexist, or they enhance each other? So try to answer this question was one of the motivation for behind this our work. Okay. 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 So as I said before, charge density order was initially proposed as coming from the electron-phonon interaction. But also, it can, this interaction, this charge density order comes from the electron-electron interaction, mainly from the Coulomb repulsion, as was reported, for instance, in these two papers here. So these papers here, they have a two-band model, okay, on a square lattice, okay, and where they consider that charge density wave appear from this Coulomb repulsion here. This is a local Coulomb repulsion, okay, but without considering superconductivity. Okay, but now we are going to generalize this model, okay? So we have a two-band model, still in a square lattice, okay? So this term here is a large band, kind of a C band. This is a narrower band. This is the relative shift energy between the bands, okay? Can resemble, for instance, the experimental, the chemical substitution used by experimentalists. This is the chemical potential in standard form. This is the on-site hybridization, okay? For us, resemble pressure. This charge density order comes from this term here for this on-site Coulomb repulsion as the previous work, okay? And superconductivity comes in the standard form from this term here. All right, so this is our model. Remember, it's in 2 dimensions. Square lattice. Okay, some parameters of the model. We introduce a charge density wave order parameter from this average value of the electron C and D. Okay, this delta C or delta D are the CD double order parameter. This is the equation for this order parameter. It's important to say that we consider magnetic solution in this problem. Okay. And this is the superconducting order parameter in a standard form. Okay. All right. Well, in order to diagonalize this Hamiltonian, we write this Hamiltonian in a matrix form. Okay. So by using the number spinor basis, the important thing here is this radio here, this gamma, is the relation between the hopping of the bands, and also can be related with the effective mass of each electron, right? Okay, so this is the Hamiltonian in a matrix form. And now we are to move to get some numerical result. How? Well, this is by using the Bogoulius-de Gennes transformation, we have the diagonalized Hamiltonian, right, in this form, standard form, right? And this guy here is the eigenvalues of the matrix that I showed you before. Also, the free energy is put in this form, and we can get all the parameters that we introduce in our model by a minimization of the free density energy. So by solving all these equations here self-consistently, okay? All right. Okay, let's go to the results. First, in the commensurate regime. Remember, we are in 2 dimensions, it's a square lattice, so the modulation with vector is pi over the lattice parameter. So just take a look first for this. This is a experimental phase diagram, very nice experimental phase diagram for a Team D compound, lanthanum, platinum 2, silicon 2. And we can see here that for high temperatures and weak pressures, well-established charge density wave order, but at low temperatures, there is a kind of coexistence between CD double phase and superconductivity, right? If pressure increase, this CD double transition temperature decrease, and suddenly around maybe 2.4, maybe something like this, it suddenly goes to 0, indicating that a first order transition has occurred, okay? If the pressure increases even more, we see that the superconducting phase still survives, while the charge density wave order is completely suppressed. All right, this is our results, okay? This is our published in this paper here, and you can see some similarities between these phase diagrams, okay? So from this similarity, we can conclude that our findings are at least qualitatively very similar or quite similar to the experimental results. All right, so this is for the commensurate regime. What about the incommensurate regime? So in this case, we want to answer this question. Is the stable solution a mixing phase for superconductivity, and this is incommensurate charge density wave? Okay, to answer this question, we are going to do here is analysis of the minimum of the free energy density in this column here, okay? And also an analysis of the charge density wave order parameter and the superconducting order parameter here, okay? Starting from the row, the up row here, okay? For this temperature, for instance, 0.01, okay? We have this density plot, okay? As a function of Qx and Qy. What does Qx and Qy? Well, there are the components of the wave vector modulation. This wave vector modulation, that's right. So, starting from this panel for this temperature, we see that the most stable solution, the minima of the free energy density, is just around Qx1 and Qy1. So it is, for us, is indicating a commensurate regime is established, okay? This result can be confirmed from the charts, from the CD double order parameter analysis, and you can see here, we can observe that we find a very robust values of the CD double order parameter. As on another hand, from the analysis of the superconducting order parameter, we see that this is mainly 0. So from this first row here, we can conclude that our model predicts a commensurable charge density wave phase, at least for this temperature. Okay. If we lower the temperature, for instance, for this 0.06, we observe from the analysis of the free energy density that the minimum of that is no longer in 0, in 1.1, in 1.1 here. Okay, so it is slightly different of this value. Okay, this indicating for us that incommensurate charge density wave occurs. This result is confirmed by this analysis of the CD double order parameter. Okay, and again we find that the superconducting order parameter remains 0. So from this analysis here, we conclude that, at least for our model, the system is in the incommensurate charge density wave state. Just if we even lower more the temperature here, for instance, for this value here, it's almost 0, okay, we get that we have still an incommensurate charge density wave solution, but superconducting is no longer 0. Okay? So from this panel, we can conclude that we have a coexistence between charge density wave, incommensurate charge density wave, and superconductivity. Okay, the question now is what we can do with all this analysis of the minimum of the free energy. Well, we can construct several phase diagrams, okay? So for instance, here, we plot, sorry, I think it's, okay. The temperature as a function of band filling, okay? And here below, we have the temperature as a function of the relative shift energy between bands, okay? And we can observe from both phase diagram the diverse phases that appear, like incommensurate charge density wave, commensurate charge density wave, superconductivity, and even the coexistence between these phases. Okay, just to conclude, let me talk briefly about this result here. This result here was published in this paper for these guys, okay? And they study the interplay between charge density order and superconductivity, okay, on a square lattice like us, okay? But when some difference. For instance, the model, they use just a one-band model, okay? And another difference is that for these guys, charge density wave comes from the electron-phonon interaction, rather than the electron-electron interaction like we have considered. But despite of this difference, we can see that both models find some similar phase diagram, at least when we plot the temperature as a function of the band filling. Okay, perfect. Just let me show you. That is 60 minutes. That's right. Let me show me conclusion. This is after analysis of the free energy. Okay, we discovered that there are certain parameters condition and incommensurate charge density wave emerge at low temperatures and can coexist with superconductivity. Also, away from the half filling, our finding aligns qualitatively with previously reported results observed in compounds that undergo a discontinued disappearance of the charge density wave transition, indicating a first-order phase transition. And also, besides these findings, we have obtained diverse phase diagrams using our model. For the time, I couldn't show you. For instance, hybridization and color repulsion, or as a function of the band filling, among others. So, if anyone have would like to more details about our result, please don't hesitate to ask me at any time during the event. So thank you very much for your attention.
Thank you. We have time for one or two questions.
Quick question about your, when you show the gap function in Q space,
yeah.
If you can go back, just...
Of course.
Yeah,
right.
So I'm a bit confused by panel I, because it seems here that the gap is essentially, if I look at the color scale, is almost K independent. Like, I would expect it to have a peak at Q equals 0 or at finite Q, but it seems that there's no peak. It's just...
Yeah, it's kind of independent. Yeah, right.
So what does it mean? It means that it's like local?
Well, good question. The point, I think, is, okay, the way we decouple the superconducting term is like a BCS. If you remember, maybe in this, the first experimental phase diagram I showed, I said that from the experimental analysis, they found that the superconductivity can be explained by the BCS framework. You're right? Okay? So, okay, it's a toy model. Okay, so we use just a kind independent delta.
Oh, I see. Okay, I get it. Thanks.
Just for instance, I can give another example. The hybridization in normal condition should be CAD dependent, right? Right, and give some symmetry and maybe anti-symmetry hybridization and that's on, like pignetized, for instance, right? But also, even in this case, is also kind independent as well.
Okay, I believe our time is over now. So if you want to talk with Daniel, you can do this later. So this section is over now. Thank you.